I welcome everyone to this video. I am Mr. Ish. Thank you for joining me. We're looking over here at total differentials, and partial derivatives are involved in that. And this is an interesting topic. If you are looking at a function and the item you're looking at z, it is made up of two independent variables x and y, then you know the dx, your differential with respect to x, is equal to change in x, and likewise the differential with respect to y, dy, is your change in y. What exactly is a total differential? Total differential, when you're looking at here at a function with respect to z, is dz. It is equal to your sum of your partial differentials. What does that mean? Your total differential dz will be equal to your sum of your partial differentials. Look, I am looking here with respect to x a partial derivative, with respect to y a partial derivative, attached to their appropriate partial differentials dx and dy. When you add up these partial differentials, you'll arrive here at a total differential. How this relates or how this means is best exemplified through good examples, and I'll show you. Once you see these examples, you'll see how this particular item right over here comes into play to give you this right over here. And this right here is the main essence of this video, but we need to look at good examples to really understand and appreciate this. Let's start over here with our first example. When you're looking at total differentials, they're really interesting in terms of applications for approximations and for error analysis. I'll show you examples of both, but here we're looking at an approximate calculation which will look at total differentials. You're looking here at an approximate area. You have to determine the approximate area. Determine the approximate area of a rectangle. If you know x is equal to 35.02 units, what are those units are, and y is equal to 24.97. This can be length and width. I'm just calling it x and y. You know for a rectangle, area is equal to x and y. Now think back to the basic definition or the formula of your total differential. This right here is my z, and I'm looking at my x and y. I am really interested in this because it's going to help me determine the approximate area. You know you can just literally multiply this by that and you're getting your actual area, but we're looking here at approximate area. How can we do it? Think back to your very first screen where we were looking at dx's and dy's. If I were to say x was equal to my length, which is 35, then I know my dx, my delta x, is equal to 0.02 plus 0.02, right? Because this plus this will give you this. If I said y was equal to, I have a 24.97, I'm just rounding it up to 25. Then I know my dy, my delta y, is equal to what? It's a minus of that, it'll be minus 0.03, because this plus this will give me that. Now, look over here. Before I show you this, let me just show you what was the original representation. Your total differential is equal to your sum of your partial differentials. You had a partial differential here with respect to your x and then dx. Then you had a partial differential with respect to your y and then a dy. I have my x's and y's and all of that. I have everything laid out for you, x's, y's, your delta items. Now, if I'm showing you this right here, modify what you see here for what you are dealing with. What are you dealing with? Area calculation. I have an area here is equal to x and y. I know if I were to do a derivative of this, let me show you something before I actually bring it into the actual form. If I were to do the derivative of this by rule, what do you have? You'll have y times the derivative of x plus I'll have x times the derivative of y. That'll give you a derivative here. This right is your product rule. Now consider what I just showed you right before this, the total differential formula. If I were to do the total differential formula, you are looking here at the dA. It will be equal to what was that? The partial derivative with respect to your x variable and dx. I'll have a partial derivative with respect to my y variable and dy. Now these are equivalent to each other, and I'll show you exactly why. If I were to do the partial derivative of this right here, when I look at this expression right here, what is my partial derivative with respect to my x variable? The one variable is differentiated, the other one becomes a constant. When you're looking here at your partial derivative with respect to your x variable, what do you have? The y is held constant, x is differentiated, you're ending here with just a y. When I do my partial derivative with respect to the y variable, now the y variable is differentiated and x is treated as a constant, the y is equal to 1, then you're left here with x. If you substitute these items right here, look exactly what happens. When I substitute these items here, what will I have? I have a partial derivative with respect to my y is equal to my what? It's equal to exactly the outcome of that partial derivative computation, which is an x. When I do the partial derivative with respect to the x variable, it is being brought right here, you're ending up with the outcome of that computation, which is y. And this right here is suddenly equal to exactly what you see over here. When you are looking at total differential calculations and you're performing those partial derivatives involved, it's really doing nothing other than just your basic derivative procedures, and you'll see that to be true. The partial derivative calculation just helps you get through what you need to do. Now what do I do with this? I am looking here for this item here. I have my y, dx, x, and dy. I have them right over here. Let's bring them out. I have a y which is equal to 25. I have a dx which is 0.02, a positive 0.02. Then I have an x dimension which is 35. Remember, I have not said units. My units here are just units. It's not centimeters, meters, or whatever. And my dy is equal to minus 0.03. And we're still doing an approximate area calculation. Now you have to bring out a calculator and do this. Let me compute this. I have a 25 times 0.02 plus a 35 times minus 0.03. I have here a minus 0.55. I'll put it over here. This is not my end result. This is only giving me my total differential. But what does a total differential represent? It represents your delta. But delta, your change in what? Your area. What will be your approximate area? Your approximate area will be equal to A plus dA. What's my A? It's certainly not the product of these, but it is a product of your estimated length and width. 35 times 25. What's 35 times 25? I have 875. So let's put that here. 875 plus my dA, which is really a minus 0.55. Compute this. You minus here a 0.55, and I will have here 874.45 units squared, because we're looking here in area. I'll just put it down over here. This right here was equal to 874.45 units squared, and it will be correct. Let's not write over our original writing, and here it is. If someone were to give you dimensions, x is equal to 35.02 and y is equal to 24.97, these are your lengths and widths, and someone asks you to calculate the area, you know you multiply those two, that's your true area. If someone asks you to approximate the area, you make an approximated length, you make an approximated width, you determine your deltas, your variances, you run them through this procedure, and now you've arrived here at an approximate area. What is the importance of this? Perhaps it's not as relevant for something like this, but when you're looking at things which are more complex, where multiple variables are involved, then this entire procedure becomes quite relevant. You're doing here a basic approximate area calculation. This 874.45 units square will be correct, and it will incidentally be very close to the actual value if you were to multiply both of these. This question here comes to an end, but you're seeing how partial derivatives were involved in your total differential calculation, which is right here. This right here is your total differential. We'll be looking here at multiple examples, and we'll work our way up. Look at this example. We have to compute the approximate volume of a box. This box will be a three-dimensional solid. It has a square base with dimensions 8.005 units. I'm not defining them, and a height 9.996. You know what a box looks like? It's like a rectangular three-dimensional solid right here. This right here is what I'm looking at. I have 8.005 this way, 8.005 this way, and I have a 9.96 units that way. This is what I'm doing. I'm looking here at the approximate volume. I'm to compute an approximate volume. You can symbolize the approximate volume like this if you want. It's not official lingo or terminology, but people understand it to be that. We're looking at that. We're going to compute this. How will we do it? I have here length, width, and height. If my length is supposedly 8, my width is equal to 8, and my height is equal to a 10. I'm going to round it up to a 10. What are my DL, my change in length, my change in width, and my change in height? You're just looking at this. If this right here will be 0.005, this plus this will give you that. This here will be 0.005. This plus this will give you that. And this right here will be what? You'll do here minus 0.004. 10 plus minus 0.004 will give you 9.996. Now how would we run this through your total differential? My total differential, the variable here that I'm looking here as volume, is equal to what? I know volume is equal to length times width times height. Anytime I do a partial derivative calculation, imagine its length. This is derived, these are held constant. It will be equal to what? Your partial derivative with respect to your length, then dl, plus partial derivative with respect to your width and dw, plus partial derivative with respect to your height variable and dh. So this right here is it. And the calculations are actually quite easy. What is my partial derivative with respect to length? When you know volume is equal to length times width, I'm differentiating this. These are constants, so the derivative of L is just a 1. I'll have over here a WH. What's my DL? You're given that. Anyhow, we'll put DL here. What's my partial derivative with respect to my width? Derive width, hold the other two constants. The derivative of width is equal to 1. This is a partial derivative coming through. It will be equal to what? An LH and then DW. What's your partial derivative with respect to your height? This is differentiated. Everything else is treated as a constant. I'll have LW and then DH. Now I know my dV is equal to what? I plug in the items. I have LWs and H's. I have my DLs, DW and DH right over here. What's my W and H? My W and H is 8 times 10, which is an 80, and my change in length is a times 0.005. Plus, what's my LH? LH is 8 times 10, which is an 80, and then again DW here is a change 0.005, your delta W, which is exactly that. LW, that's 8 times 8, which is a 64, and my change in height was a minus 0.004. I have to compute this. This will be my dV, my change. And let's bring the answer here. Let's do this computation. This 80 times 0.005 times 2, because these are identical, we'll just do it that way. 80 times 0.005 times 2 plus 64 times 0.004 minus, I have here 0.544. That is giving my total differential with respect to volume is equal to a positive 0.544. What is my volume? My volume here will be equal to what? It will be, let's just say, volume plus dV. What is this volume right here? It's equal to my these approximated values, or my these estimated values, or my rounded values. 8 times 8, 64 times 10 is a 640 plus 0.544. When you add them up, you'll have 640.544 units cube of that rectangular box, and it will be correct. And we've demonstrated by total differential calculation, but it also involved partial derivatives, as you saw right here. These are the partial derivatives. The sum of your individual partial differentials coming through will give you your total differential. Then you do something with that, and what you do with that total differential depends on what type of analysis or question you're looking at. Let's look over here at an error analysis question. We have to find the maximum possible error and the error percentage if, with regards to a volume of a cylinder pi r squared h, I have these dimensions. Radius is equal to 5 units plus or minus 0.05 in terms of an error that can come through, and the height is equal to 12 units plus or minus 0.1 in terms of an error that can come through. These error amounts are here in actual degrees of units. If I have 5, then I have a plus and minus 0.05 units. Likewise, height is 12 plus and minus 0.1 units in terms of how poorly or well you read or calculated your dimensions using a ruler or whatever. These are not percentage values, these are actual values which you would add to this or subtract. Anyhow, how will we do this? We have here a total differential calculation to do. Your error percentage will be equal to what? It will be equal to your, in this particular case, this over this times 100. Your total differential in terms of the amount of error that could have played through divided by a total volume times 100. You'll see it when it comes through, it makes sense. And I'll show you exactly what I mean. How will I start? I'm looking here at radius and height and this. When I do this, the total differential with respect to the volume, you know pi in all instances is equal to what? It's a constant. I'll be looking here at a partial derivative with respect to my radius, and then I'll do dr. Then I'll obviously do a partial derivative with respect to my height, and I'll have here a dh. Now when you are doing this calculation, don't worry about the pi, it'll automatically make its way in. How will it? Look here at this partial derivative with respect to my radius. When I do this, the radius is differentiated, everything else is treated as a constant. I'll have a pi, I'll have a h, then I'll have a 2r. When you put it together, you have a 2 pi rh. When I'm looking here with respect to my height variable and doing a partial derivative, now the height is treated as a variable to be differentiated, everything else is constant. The derivative of h is just a 1. I have here a pi r squared. When I bring in these items, what do I have? I know my this item right here, the partial derivative with respect to your radius is what? It will be a 2 pi rh, and then I'll have here my dr. When I do this item right here with respect to the partial derivative and the height, I have here pi r squared, and then automatically I also have my dh come through. You have these values here provided. Everything is right over here. R with the delta items with it. The delta items that you're seeing here are right over here. Here's your delta items plus and minus. Before we continue on with this, look right over here. I've identified this because I'm going to run this through the product rule. You know the product rule is f times g function derivative plus g times f function derivative. Just run it through that. You have here a pi pushed out. I'll run it through this. This is my f function right here. Here's my g function, and let's see what happens. I'm doing f function, which is r squared times the h function derivative. We'll just write that as dh. Then I'll do the g function, which is h times the r function derivative, which will be a 2r, and then I'll have a dr, and then you open this up. What will you have? You'll have a pi r squared dh plus you'll have a pi times multiply this, will you have a 2 pi r h dr. Now compare what you're seeing over here with what you're seeing over here. It looks exactly the same. I have a dh with a pi r squared, and you see that here. I have a dr with a 2 pi r, that you see over here. What you're seeing over here is partial derivatives are technically just disguised. They're actual full derivatives. There's no such thing as that you're doing an incomplete derivative. You're still doing a complete derivative. The only reason why it's called a partial derivative is because you're not treating all the variables equally. At a particular point, one variable is differentiated, the other one is not treated equally because it becomes a constant. Hence, it's a partial derivative even though you're doing a complete derivative calculation. So never get confused by that point. Let's come back to our original item over here. My dv is equal to what? I'll bring in these items. This right is my total differential. I have a 2 pi, and my r was equal to a 5, my height was equal to a 12, and my dr is equal to a what? I'll do 0.05. And then pi r squared, I have a pi. Then I have here r squared, which is 5 squared. And then my dh is equal to a 0.1. Compute these. What will you have? I won't compute the pi. I'll just isolate the pi, and now I'm looking at 2 times 5 times 12, which is a 10 times 12 is 120 times this 0.05, plus I'll have here 25 times 0.1. I have 120 times 0.05 plus 25 times 0.1, 8.5 pi. My dv is equal to my 8.5 pi, and that will be correct. What does this mean? It's your total differential. My total differential is equal to 8.5 pi. But how do I actually bring this into sense? In this particular case, my total differential, since we're running the errors with it, it is giving me a total differential which equals to what? My maximum possible error. In this particular case, this dv represents a total differential, but total differential with respect to an error. This is the maximum error I can have in this cylinder computation. But what is the percentage of error? This answer has been solved. It's 8.5 pi. That's the maximum error. But what's my error percentage? You will do 8.5 pi divided by your volume. What's your volume? Run it through here. Pi r squared is 5 squared times height, which is going to be a 25 times 12 times pi. You're running it through the volume. 25 times 12, I'll have here a 300 pi. That's your volume multiplied by 100. These will cancel out. I have the zeros cancel out. I have a 8.5 divided by 3, and you'll compute that. What will that be? It'll be equal to 2.833%, and that right there is your error percentage. What's your maximum possible error? It's 8.5 pi, because here your total differential is giving you an error calculation. What's your percentage of error? You have it right here. Your dv, your maximum error divided by the total volume times 100, and it will be correct. It's 2.833%. Let's look over here at an electrical resistor. Power is equal to E squared over R, and in watts you have here E value, which is 200 volts. You have R, your resistance 8 ohms. How will the power change for this system if the E is decreased, the voltage is decreased by 5 volts, and R is decreased by 0.2 ohms? The resistance is decreased, your E value is decreased. How will your power be affected for this system? How will you do this? Now consider what I have over here. I am looking for dP. How will the power be changed? A total differential. If E is decreased, I know that's my dE is decreased by what? 5 volts. I'll just say minus 5. And my resistance is decreased. dR is equal to what? 0.2 less minus 0.2. I have those. how will the power change for the system. And you have seen all of this come through, and I've translated for you on the side over there. I don't need this because I'll just erase it from my work. Let me show you something here. I'm looking here in terms of a derivative of this using the quotient rule. See what happens if we run everything through the quotient rule. Then I'll show you how everything runs through the partial derivative and the total differential way, and you'll see them to be the same. I have f and a g. G here will be, I'll see over here in r times the f function derivative, which will be 2e, and then you're looking here at a de because that's the derivative of your f function minus f, which is an e square, times the g function derivative. The derivative of r is 1, but you're looking here at dr divided by here r square. If you separate everything across their individual denominators, this right here is a quotient rule. Not what happens, I'll separate these along their denominators. I have a 2er over an r square and then a de minus e square dr over r square. If I simplify this, because I have an r here, this is what I have. I have a 2e de over r minus e square dr over r square. Quotient rule has showed me and brought me to this. So now let's do everything using partial derivatives and total differentials. You know this is our variable, the z variable. Here it's p for the power. I'll do a partial derivative with respect to my e, and then de. Then I'll add to that. These are my sum of my individual partial differentials adding up to my total differential. Then the partial derivative with respect to your r variable, and then dr. What exactly are these items? Now compute those. Now let's find these individual partial derivatives. The partial derivative here with respect to the e variable, the r is treated as a constant, will be a 2e over an r. Partial derivative with respect to the r, the e is treated as a constant, it will be an e square. You're doing a derivative of r to the minus 1, it will be minus r to the power minus 2. It will be a minus e square over r square. Bring these in with these items you see over here. I have a de and I have a dr. De, this minus, I'll just put it right here, and a dr. Now compare what you see over here with what you see over here. It will be the exact 2e de over r minus e squared dr over r square, and it's exactly the same. The quotient rule gives you exactly what you would get from your partial differentials coming through. Why? The partial derivatives are not any less of a derivative. You're just looking at your entirety of your system, but looking at it partially at a time, because one variable is treated as a variable for differentiation, the other one is treated as a constant, but you're doing this exact same procedure with the other variable. Then you're doing some of those individual partial differentials to give you your total differential. Hence the outcome of this is equal to the outcome of your quotient rule. You see it over here. Now plug in your items. We're doing here a determination of by how much is the power of this system reduced if the e value was dropped and the resistance was dropped. Dropping resistance is actually a good thing, but then also dropping the voltage is not necessarily a good thing because you have less coming through. Now how will we compute this? We'll plug everything here. I have a 2, my e value here is a 200, my de is a minus 5, and my r over here is an 8. Then I have an e square, which is a 200 square, times my dr, which is a minus 0.2. We don't need that extra. And then divided by r square, which is an 8 square. And we'll just compute this and arrive at our end result. And let's compute these. Let's get a figure here and get a figure, and let's see what the item is, our end result. 2 times 200 times 5 minus divided by 8. I have here minus 250. This will be a plus. This minus will become a plus. 200 squared times 0.2 divided by 64. 200 squared times 0.2 divided by 64 plus 125. What's my end result here? It's a minus 125 watts. What is this telling you? This is telling you for this system, P equals E square R, with this voltage 200 coming through and resistance of 8 ohms. If this was decreased by 5 volts and this was reduced by 0.2, the resistance was decreased by 0.2 ohms, your power output will be decreased by 125 watts, and it will be a correct answer. And we've done this using total differentials. So that's it for this video. Thank you for watching.